So this is the third installment of my lecture on architecture and programming models for GPUs and coprocessors. And we're still talking about performance of computer programs. Before we start, let's just briefly recap what we talked about last week, and most specifically, where we currently are in our discussion about concurrency. Last time I showed you this illustration where we had this spectrum of different types of concurrency. We talked very intensively about software pipelining. Today, we will take a step back and talk very briefly about hardware pipelining and also about something that is called out-of-order execution. We will only very briefly and very superficially touch those topics because honestly, arguably the most important topic when it comes to instruction level parallelism is software pipelining, and we talked a lot about that, and so I also decided to place a strong emphasis on software pipelining. And after we finished our discussion of instruction level parallelism, we will switch over to types of parallelism that are more exposed, that are actually more exposed to the programmer. Like we will talk about Zimbi registers that I mentioned a couple of times during the sessions last week, and we'll finally find out what that really is. And then we will talk about multithreading and multi-core systems and multiprocessor systems, and we'll talk about programming models. And that'll probably be it for today. And next time we'll have a quick look at programming of network systems. Like we'll have a look at a very specific API that is used in high performance computing, and that is called the message passing interface. But that we'll probably not have time to look into today. But we'll talk about that next time. When we talked about software pipelining last week, we were in a constrained setting with limited resources. Like the resources that we discussed were ALUs or MMUs, and the compiler might be presented with other resource limits, like a limited number of registers, for example. When talking about the hardware level, things are even more complex. Like when we were talking software pipelining, we assumed that we would pipeline individual instructions based on resource constraints, and now on a hardware level, we're assuming that we can even pipeline instructions based on the phase of retirement they are currently in. So when we retire an instruction, the first thing that we do is we fetch the instruction from memory or from a buffer, and then we decode the instruction, and then we fetch all the operands that are necessary to execute the instruction. So we're basically filling registers with content, and then eventually we will execute the instruction. And those phases can actually be pipelined too. And a concept that is very much related to hardware pipelining is out-of-order execution. And out-of-order execution is a functionality that that some CPUs implement. Most prominently, some Intel CPUs. And the idea here is basically that we can, at runtime, reorder instructions when there are no data dependencies, like that would keep us from reordering the instruction. Like in the simple example here, we're first loading something from memory to register R0, and then we are performing an addition. Like we already have some other value that was previously written to R4. And then we perform an addition where we have a data dependency, and so that means we have to execute the load instruction first, and only then can we retire the add and the first add instruction. And then this is followed by a second add instruction, but that second add instruction doesn't have any data dependencies with regards to either the load or the addition from before. So that means we're generally relatively free when to execute that function.
instruction. No. So what we also can assume is this is again an example, but it's quite often the case that memory movement takes has higher latency than arithmetic, and let us just assume, for the sake of the example, that there's a 20 clock cycles latency for the load instruction and a 4 clock cycles latency for the add instruction, and that means when performing those two instructions with the data dependency, we're stalling the pipeline. You know? And for those reasons, it would be advantageous if we were able to maybe while we are loading, already schedule the second addition, yeah, and then we were maybe already finished with the second addition, and then the operands for the first addition are available, and then we would execute the first addition, and basically would have used a reordering of the instruction stream to effectively hide latency. And the reason why I said earlier that out-of-order execution is so much related to hardware pipelining is the fact that the principle here is based on pipelining with regards to the different retirement phases of an instruction. Like the idea is really that we have the load instruction, and then we have fetch and decode, and fetch and decode is followed by a significant wait time where we're waiting for the operands to become available. So the instruction potentially goes through a cache hierarchy and then goes into memory. And there's a significant latency, but that latency actually manifests here while we're waiting for the operands to become available. And this wait time, this extended phase of the load instruction basically gives us the possibility to hide latency and to schedule instructions in between. As the arithmetic instruction might, for instance, have a significantly shorter wait time than the load instruction. So again, out-of-order execution is a technique that is implemented by the processor. So there are dedicated functional units that are integrated into the processor that will, at runtime, like when the instructions occur in the instruction stream, will try to employ heuristics that allows the processor to reorder instructions. So out-of-order execution is a latency hiding technique that goes hand in hand with hardware pipelining. Out-of-order execution requires a dedicated functional unit on the processor or on the CPU, and obviously such a design also has its drawbacks. A dedicated functional unit that reorders the instruction stream at runtime obviously potentially adds to the complexity of the processor design. And therefore, there are some vendors like Intel that implement out-of-order execution in some of their processors, and other vendors don't implement out-of-order execution. It is worth noting that neither of the coprocessors that we will discuss implements out-of-order execution, so GPUs usually don't implement out-of-order execution. GPUs have other latency hiding techniques, and we will discuss those to some length in the later sessions of this lecture, but they don't use out-of-order execution. Let us now talk about a topic where the programmer has much more influence about what is happening. The topic we're now talking about is the one that I teased once or twice in the sessions last week, and the topic is Zimbi and vectorization. And Zimbi and vectorization is really all about the data path of the data items that the data items take when going through the instruction stream. Like before, we were assuming that we had multiple instructions, and we had this conveyor belt metaphor where we had several stages, like instructions that perform some operations on the data path, and then the data items are passed through and passed to the next instruction stage. via the conveyor belt, and until they are like all the instructions are retired, and then eventually when the program is finished, the data path of the individual items is finished too. And we also saw how we can make use of instruction level parallelism by pipelining those instructions, and we will now see a parallelization technique that also happens on the hardware level, but that actually happens on the register level. So, and for those reasons, it's much more controllable by the programmer through certain programming techniques, and also through certain programming APIs and compiler extensions. And the idea is really that we don't just have one individual scalar data item that takes the data path, that goes through that conveyor belt and through those several pipeline stages, but that we have registers where there are multiple scalars that fit into one register. Where we before had general purpose registers, where like a 32-bit floating point number would fit into the register, like a single precision floating point number would fit into the register. We now have registers where multiple of those operands fit into one register, like dedicated vector registers. And those vector registers now make up the data path, and items in those vector registers are operated on concurrently. Like what happens is that our data items go through the several stages, and they do so in lockstep. Meaning there is no weighting of data items for each other, but they're literally all in the same register. And literally all modern CPUs support vector instructions. And really, when you're a programmer and when you want to make optimal use of your CPU, you have to take care of vectorization to some extent. And there are several techniques that we will discuss that help you to make use of vector registers and of vectorization. And the most accessible probably technique, or the simplest means to make use of vectorization, is to just instruct the compiler to optimize, set flags that the compiler applies optimizations, and an optimizing compiler will then try to auto-vectorize your code. We will have a look at how that works later on, and it also has several drawbacks, because this really only works in some very constrained settings. And therefore, it is on the one hand often required to restructure the code so that the compiler has more opportunity to actually auto-vectorize the code. And usually, when dealing with vectorization, really one has to explore the generated assembly output to make an assessment of what is really going on. Yeah? And then there are explicit approaches to program vector registers and vector extensions, and we will also discuss those very briefly. Let us have a look what happens on the instruction level. And the example I'm showing here is from the SSE instruction set. The instruction set that was implemented by most Intel and AMD CPUs over the last 20 years. As you can see here, I have those special instructions, and those special instructions are suffixed with the suffix PS, and the suffix PS means we have a pack, and pack refers to that we're using vector registers, and the S signifies we're dealing with single precision floating point numbers. Yeah. And then, as you can see, I have those vector registers, like with SSE, they're usually called XMM0, XSM1, XSM2, and so forth. And you can see how I fill this XMM0 registers with all twos. Like the set function is basically like a mem set function where I can pass a scalar value, and then this value is used to fill the registers. And then you can also see that I'm using a load instruction to fetch data from memory into registers. Yeah? So I have my my 128-bit register, like each of those entries in the vector has 32 bits. And then I use the load instruction to load data items from memory, like to fill it with memory. So like this is basically a constant where the whole register stores the value 2.0 on each lane, on each Zimbi lane, and this is a load instruction from memory. Yeah. And then you can see like this happens in the first clock cycle in our example, and then you can see that I perform a multiplication, and at the same time I also perform another load. And you can also see that all those instructions operate on the whole vector of scalar values. So when I execute this, or when I try to retire this instruction mul of the multiplication, that actually operates on the whole vector. Yeah? So and then I have my next load, and then I have an addition that also happens in vector fashion, and then eventually I store my result. And you might recognize this simple program here. This simple program here again is the Zaxby loop that we discussed earlier. So in the example, what I showed you is the SSE instruction set. SSE machines have 16 128-bit wide Zimdi registers that are labeled XSM0 through XSM15. And then there are designated vector operations like the ones that we saw before, like the add PS instruction or the compare PS instruction and so forth. And those operate on the whole packed vector at once. And there are also, depending on the instruction set, but SSE does have that, there are also dedicated instructions for integer arithmetic, and also dedicated instructions for double precision arithmetic. And when I'm using double precision arithmetic, what really happens is that I again use those 128-bit wide Zimdi registers. But now I store I don't store 4 scalar values in one register, but actually store 2 scalar values, 2 64-bit scalar values per 128-bit Zimdi vector. So SSE has in the meantime been superseded by the AVX instruction set. So most of the computers from the last 10 years, most of the Intel computers implement the AVX 256-bit Zimdi instruction set. So where we can potentially pack 8 32-bit single precision floating point values into one vector register. So 8-bit 256-bit Zimdi is pretty commonplace on the x86 architecture nowadays. ARM has a dedicated vector instruction set that is called Neon, and ARM Neon is 128-bit, so comparable to SSE. We talked about that the compiler in certain cases is able to auto-vectorize loops. And the compiler is really only able to do so with very simple loops, and most specifically with loops where there are no data dependencies. Let us have a look. Let us have a look at some pseudocode, how that works. So this is this is a pseudocode notation that I use to illustrate what's happening, and the pseudo language I am using has those vector instructions that make things much simpler. Yeah, and like when the compiler encounters a loop like this, in order to vectorize it, it first has to do two things, or it has to do a bunch of things. And the first thing that the compiler would have to do, it would have to adapt the stride of the loop. What is the stride of the loop? The stride of the loop is the stride of my loop counter. So the loop counter here has a stride of 1 because the steps that I'm taking through those vectors of length n are 1. Each time I schedule a new loop iteration, I only operate in this scalar loop. I only operate on one data item at a time. So, and as this loop doesn't have any iteration data dependencies, and as it is vectorizable, it is I can equivalently formulate this loop with a stride of 4, and then inside the loop iteration instead of only one of those computations, perform 4 of them. Like if I would write this out in C or in C++, what I would end up with would be 4 of those lines that perform those operations. So I decided for this a bit shorter notation here, which signifies we're performing the operations like the load operation and the addition and the store operation. We're performing this on 4 values at once. So the compiler will adapt the stride through the loop, and the compiler will unroll the loop body and perform 4 iterations at once. So the problem is that vector sizes aren't necessarily divisible by 4. So the compiler will then take the loop and we'll break it up into 2 loops. And we will end up with one vectorized loop where we have this stride of 4 and the vectorized operation, and then we will have a scalar loop for the remainder. And the scalar loop for the remainder just processes the remaining elements where they are not divisible by 4, like up to 3 data items. You can use this as a bit of a self check, or you can also play a bit around with this and try to vectorize this loop. And as a hint, the compiler explorer tool that we discussed earlier, that I showed you earlier, might be helpful for that. So you might play a bit around with this loop in the compiler explorer, and then try to find out if you can vectorize it, or if you can find variants of this loop that are vectorizable. Yeah, just play around a bit with the compiler explorer tool, and try to find out what type of loops the compiler can actually vectorize, and what type of loops it has a hard time to optimize and to vectorize, and maybe play around a bit with it and try to restructure loops in order so that they become vectorizable. So what we discussed before is how the compiler would vectorize a loop. So we're basically doing nothing. We're just presenting the compiler with the loop, and we're telling the compiler to apply optimizations. And apart from that, we're really doing nothing. And as it so happens, this works in some very constrained cases, and in most of the cases it doesn't really work. And most of the cases we have to go back to the code, restructure the code, make the code more obviously data independent, so that the compiler really understands it's data independent. And even in those cases where it's pretty obvious, the compiler might not even recognize that it can vectorize the code. And then there are some language constructs that help us tell the compiler what to do. And the next simpler language construct is to use pragma. So pragmas are really just hints. They're like annotations for code where I tell the compiler, like pragmas are like compiler specific hint. And with certain pragmas, I can hint the compiler that the loop that follows next is a loop that I would like the compiler to vectorize. So vectorization through annotation is the next simpler construct to auto vectorization. And in certain cases, even that doesn't help. And for cases like these, I have explicit means at hand, like dedicated APIs that help me to really vectorize myself, and then it's completely explicit. And those APIs are usually exposed as so-called compiler intrinsics. So they're not really libraries, but they're like compiler built-ins. So I can just I don't have to link with some additional library, but they are like compiler extensions. So the SSE instruction set that we discussed earlier also has these intrinsic functions, and this is what the unrolled and vectorized Zaxby loop would look like with when implemented with compiler intrinsics. Like I already simplified things a lot, in that I'm asserting that the loop is that the vector length is divisible by 4, otherwise I would have to add another scalar loop down here. So I already simplified things quite a bit, and as you can see, things are not very readable. Like this is the loop that we're discussing. So I modified the loop so that it now has this stride of 4, which is the same thing that I would have hoped that the auto vectorizer would have done. And then I cannot use those. I don't have operator overloads for those anymore. So what I'm doing here is using the set intrinsic to initialize this constant with this value a here. And then I'm loading vector contents from memory with the load instructions, with the load ps instruction, and the intrinsic that maps to this instruction, and with offsets into memory that tell the intrinsic where to load the data from. And then after I have loaded the data, like explicitly loaded the data with functions, I also explicitly call functions that directly map to instructions and that perform arithmetic. Like here I perform the multiplication, like this is the same multiplication as this one here, and then I take the result and feed that result, and I feed the content of the 128-bit register Y4. I feed it into the add intrinsic, and then I finally store the value of this register Y4. I store it to main memory. Like this is still on a higher level than really programming this with inline assembly. Like I could actually have included inline assembly here. Those intrinsics are compiler checked, so the compiler will recognize when I'm doing something wrong here, like when I'm introducing syntax errors. Like when I enter inline assembly here, this is really just text to the compiler that is evaluated at runtime. And what I also don't have to take care of is register allocation. Like the registers here are really just variables, and I can have any number of those variables, and so I don't have to take care of in which XSM0 or XSM1, etc. the content of the register will end up in. This is taken care of for me. So it is quite explicit when I'm doing here. It can actually be more explicit when I use inline assembly, but it's actually quite an explicit way of programming those vector registers. A bit of terminology. When I'm talking about Zimbi lanes, this is really the data path that the data items take. And when I say Zimbi width, that means this is the number of, when not mentioned otherwise, this is the number of 32-bit single precision scalars that I can pack into a single vector. Like we learned before that some instruction sets also allow us to pack double precision vectors into a Zimbi register. And when I'm talking Zimbi width, and people are talking Zimbi width, like when they're saying SSE has a Zimbi width of 4, they are referring to 32-bit single precision scalars. CPUs have this very explicit model where you can explicitly program Zimbi. And we will later find that other architectures behave very similarly. Like what you can an important observation about Zimbi is lockstep execution. Like all those operations are performed in lockstep. There is no concurrency in a sense that one operation waits for the other, but it is a single circuit that operates on this whole vector of data items, which is quite different from threading that we will discuss later. And this characteristic, even if not directly exposed to the programmer, is inherent also inherent to all the other architectures that we will discuss later. Like we will discuss GPUs later, and we will discuss how threading works on GPUs, and you will see that GPUs have a less explicit model where vector registers are exposed, where execution is performed in lockstep, but where the Zimbi width isn't as prominently exposed as with the Zimbi programming models that we just discussed. Like the fact that SSE has a Zimbi width of 4 is very explicit here, because we had to modify loop strides, and we have to take care of that loop counters or vector lengths are divisible by the Zimbi width, and if not so, we had to introduce scalar loops to process the remainders. This is very explicit, and we will also later during the lecture encounter other programming models where Zimbi and lockstep execution is important, but where the Zimbi width isn't as explicitly exposed as in this case. Some best practices: we should in general try to let the compiler optimize as much as possible, because this is the most scalable and the most convenient way to make use of vectorization. This is also the most cross-platform way of performing vectorization, because as soon as we start using intrinsics or even inline assembly, we end up with code that isn't cross-platform anymore. SSE code will not be executable on an ARM CPU, and and obviously we prefer if our code can execute on any platform and not only on one. We will we discussed only very simple examples here. We discussed loops with no data dependencies, with no inter-iteration data dependencies. But in particular, our loops had no our loop bodies didn't have any branching. And when you're in a setting, say you have a simulation, and the simulation is like you have a Monte Carlo simulation, and at some point the data path diverges in a sense where certain data items just have finished execution. Some data items are still operated on, and other loop iterations just have finished. And this makes makes programming of Zimbi units much harder, because in such cases, what we have to do, we have to mask out certain Zimbi lane from execution. So we'll set some flags somewhere that not 4 Zimbi lanes will participate in the operations, like in the arithmetic operations that are to follow, but only 3 of them. And with that, we obviously also reduce the effectiveness of the operations, as we're now using a 120-bit Zimbi register, but we're effectively only using 96 bits of those registers, right? And in the extreme case, we end up with Zimbi registers being used that have a Zimbi width of, say, 4, and only one of the data items in the Zimbi vector is actually participating in the operation. And therefore, Zimbi programs are very much prone to starvation. And we talked about restructuring code, and we talked about divergence before, and we talked about divergence in particular when we talked about caches and cache lines, and there I introduced this concept of sorting and compaction, and I also told you there are other techniques that are similar to that. And in this context of Zimbi and vectorization, those techniques are also very important. As you can imagine, it might be in certain cases be worthwhile to at some point stop Zimbi execution, and then reorder the content of Zimbi vectors. So in a hope that in a hope that I can reduce fragmentation. Fragmentation in a sense that I can shuffle content from some SIMD vectors into other SIMD vectors and then free registers. So now that we understand what SIMD is, let us move even further to the right of this spectrum of concurrency that we discussed earlier. What we learned earlier is that we get those additional transistors by Gordon Moore, and the hardware vendors they have to decide what to do with those additional transistors. And one thing that they really like to do is put additional processor cores onto the die, of the CPU. And then there's also a bunch of systems like typically HPC or server systems that even have more than one processor deployed to the mainboard, like 2 or even 4 processors. In theory, those cores and those processors, they can act independently of each other. Like when we discussed SIMD, we saw that there's lockstep execution. And with multithreading, we don't have lockstep execution anymore, but the individual cores and processors operate independently of each other. And when we execute instructions from the same program, then we usually have to at some point or at some points in time, we have to synchronize the execution of the instruction. And this type of system and this type of parallelism is programmed using so-called multithreading programming models. And the elementary unit with multithreading is the thread. And a thread is just a sequence of instructions that can be executed in parallel to other such sequences of instructions. Threads are usually scheduled by the operating system, and for threads, it's important how they interact with memory. Like in a multi-threaded program, you usually have some memory that is shared between the threads, and where you have to take care of synchronization, and then you have other regions of memory that are local to the thread, where the thread has exclusive access, and where usually access is also cheaper because you don't have to take care of synchronization. There are actually multiple multi-threading APIs, even for single programming languages. Like we will focus on C++ here, and there are so many languages out there that expose parallelism through multi-threading, and they do it in completely different ways. And even C++ has like a bunch of different ways how you can make use of multi-threading and of parallelism on the per core and the per processor level, and they differ in how high level or how low level they are. And we will just discuss a bunch of the paradigms that are important, and we will do this in a bit. When we talk about those different programming models, things are mostly about how and when threads are scheduled. Like this process of scheduling a new thread is relatively heavyweight. Like when we have a program, and just imagine where our program executes serially, like for some time, and then at some point in time we decide that we want to switch to parallel execution, and then we schedule threads that operate in parallel. When we're in a serial execution mode, we have one thread, and then when we decide that we have a parallel code block, then we have then we will spawn an additional thread or even multiple additional threads. So this requires scheduling, and dealing with threads and scheduling threads is actually quite heavyweight. Like the mere operation of scheduling creating a new thread is pretty heavyweight. But then also when we have threads, like if we already created multiple threads, the operating system is relatively free to do with those threads what it wants. Like it can, for example, decide that during the program execution, it might want to migrate the thread from one processor to another. And migration in this case results in something that is called a context switch. And a context switch implies that the whole state of the thread, like all the local variables, all the register content, is copied. So copy from registers to main memory, which is on its own quite expensive. Then the operating system might decide to schedule another thread on the core that was just freed by the first thread. So again, copies from main memory to registers, which are very expensive. And during all that time, during the copying and scheduling and rescheduling, the threads so no thread can actually perform any work on the core. Yeah? So context switches, where the operating system decides to migrate threads in between cores or in between processes, are quite heavyweight, and so are operations to create new threads. And the different paradigms, how threads are used by the programmer, they differ a lot in how threads are scheduled and how threads are created. Again, the most low-level APIs are based on thread callbacks, and we're again motivating the Zaxby example from before, and the code here shows a multi-threaded program, like a program that runs in parallel, and that executes the Zaxby loop in multiple threads. So when we take a look at this example, what we see is that we, on the one hand, we have this callback function here, and the callback function receives a set of parameters. Like, I simplified this a bit here, but the callback function is passed a set of parameters, and through those parameters, the callback function can identify its shared state. Like it can identify like you pass the callback function a pointer to a region of memory, and through this pointer it can identify, and by knowledge of certain offsets, it can identify where from shared memory it shall retrieve its inputs, like the constant a here, for example, or the vector length, or the array x, and also its outputs, like the array y. Yeah, the thread callback function first is responsible for obtaining its shared state, and then it like operates on that shared data. So this is the callback function that is executed by each thread, and when we schedule those threads, we do this explicitly with this type of API. Yeah, like there's usually a function that is called create thread, and we pass it the function itself, and then we also tell it how the data is distributed to the individual threads. Like what I'm showing here is pseudocode. Like APIs that work in such a fashion are, for example, the pthread API, which is an API that is provided by the Unix operating system. The code that I'm showing here is inspired by this API, but this code, in the very way that I'm presenting it here, is simplified and won't compile. The paradigms still stay the same, and the paradigm for APIs like pthread are very similar to what I'm showing here. And the gist of what's happening being that you, on the one hand, what I do here is I explicitly say that I want two threads, and I also explicitly say how the data is distributed to the threads. Like this pack operation here kind of indicates how the data is distributed. And what you can see here is, on the one hand, that each of the thread operates on half the vector size here. So like when this thread here loads its vector size from shared memory, it will actually have only half of the ends, and not the whole vector that it operates on. And then I'm also taking care of offsets, like for instance, the first thread is passed a pointer to this array y here, and the second thread is passed a pointer to the array y, but with an offset of n over 2, like because it's only processing half of the actual data. And then I'm explicitly scheduling those threads, and then I usually with those APIs have a function where I can join those threads again, because in the end, when they finish, there's also a there's also synchronization needed. So this is the Zaxby example implemented using thread callbacks, and this is pretty much the low levels, the most low level API to multithreading that you can use. This type of API can be used from ANSI C, so it's a very low level API. A type of API that is usually only available in C++, being a superset as a superset of C, are APIs that are based on parallel primitives. The idea here is that I don't explicitly schedule threads anymore. Like I have an API where I call certain language constructs, like this parallel for function here, and the parallel for function. Parallel for function has knowledge about which value range it is responsible for, and I can access that range. I can access the current index in the range where I am in my parallel for loop. And the idea here is taking a built-in language construct, the for loop, and replacing that with a library function parallel for that behaves very similar to an actual for loop. And as you can imagine, code like this is much easier to port. Like when you have a serial code and you know that a certain loop can run in parallel, then it's much easier to take that function and reformulate it in terms of a parallel for function, than formulating it in terms of a bunch of threads that perform operations in parallel. So I actually modified the example here. This is not the Zaxby example anymore, but this is the Zaxby and reduce example. So what happens here is the actual Zaxby loop, and just to indicate that there are more parallel primitives than only parallel for, I'm in the end also reducing the result from Zaxby. So what is a reduction? A reduction is basically just a sum over all elements. Yeah? I'm taking all elements and I'm summing them up, and as a serial operation, this is an O of n time operation, and we will learn about parallel complexity later. But suffice it to say, the parallel work in order to do that summation stays the same. So when I do that in parallel, I still have to do n additions. But the time that it takes can be greatly reduced by using algorithms such as parallel reduce. And so in the end, just to demonstrate that there are other parallel primitives than only the parallel for construct, I'm reducing the Y array into its first element. So this type of programming API for threads is an alternative to callback-based APIs, and it operates on a higher level. Like I'm giving away control here. Like I'm not controlling anymore at which point in time threads are actually scheduled. Like this can be a good thing because this helps with developer productivity, but obviously, as I'm no longer in control, I cannot decide when things happen. And in certain cases, I want to be in control. Those parallel primitives usually have control layers that make sure that threads aren't like always scheduled again and again. Like when I have like say I have this parallel for loop, and then I have another parallel for loop right after. Then this type of API usually takes care of that the same threads that were used in the first parallel for loop can also be reused in the second parallel for loop without creating them anew. And this is usually done by something called a thread pool, and we will discuss that in a bit. The next level, so to say, of using threading with C or C++ is threading through annotation. And the idea here is that I take my serial code and I port it to a threading API, and I do this through annotation. So I go through my code and I go through it like sequentially in my IDE or in my editor, and I just annotate my code and I tell the compiler, again using pragmas, which are hints to the compiler. So the compiler is not really obliged, can do what it wants, but but it is a good advice to recognize those hints and make use of those hints. And the compiler, I can advise the compiler that certain loops and certain sequences of statements should be executed in parallel. And as you can see, we're on an even higher level here because we pretty much lose control over how threads are scheduled, but also about the granularity of items that are scheduled in a common range. Like with the thread callback APIs, what I had to do, I had to explicitly tile the data myself. I had to create one tile that was of size n/2 and another tile that was of size n/2, and I explicitly passed offsets into the thread callback functions. And if we go back to the parallel for construct from before, I see that I at least have control over those tiles, and that I can access the ranges. And with threading through annotation with an API such as OpenMP, for example, I pretty much lose control over the things. And on the other hand, I gain very much in developer productivity, because obviously this is a much easier way to parallelize code than using explicit APIs. So those paradigms differ a lot regarding their level of abstraction. And actually, parallelization through annotation is relatively popular, as we just have to take our serial code and then tell the compiler using annotation which parts should be executed in parallel. So when it's actually good advice to use that when we're when we're not in settings where we need the very last bit of performance. We are usually very good advised to use annotation actually. On those explicit models, they give us a bit of more control. And actually, the implicit models that have constructs that provide us with parallel primitives and with constructs such as parallel for are a pretty good common ground between the two. So now that we learned how to actually program with threads and how to make use of multi-core or multi-processor architecture, the next thing that we have to talk about is synchronization. Before we really start talking about synchronization, let's have a look why synchronization is actually necessary. And for that, I prepared this really tiny function here, and this is a parallel function. It's maybe a thread callback function that is run in parallel using the pthread API, or it's called from within a parallel for loop. So it's a function that is called by multiple threads at once, and those threads have access to a shared variable called counter, and the threads increment that counter in parallel. And this will actually call so-called race conditions. And what a race condition is, I will explain in a bit. What we should notice when we see this statement here, we should be aware of the fact that this is not an atomic statement. So that means that this statement will not compile down into a single instruction, but into a couple of instructions. Like we can assume that the compiled assembly output will look something like the following. Like we will first load the value of counter from some region in memory to a register. We will then perform an addition where an immediate addition where we add the value 1 to counter, and then we will write back the value of counter. We will write it back to memory. And so this whole statement, we say that this whole statement is not atomic. So, and the problem that really happens here is that we might load the data item from memory, and in the meantime, another thread might already modify it. So here's what's happening. Let us assume that the variable counter was never modified before, so we're loading it from memory for the very first time. So its value is 0 because that's what we initialize it with. And so for this load instruction on core number 1, everything is fine. We'll just load the variable, and we'll know the value is 0. And already when we perform the first load on core number 0, we don't know what the value of counter will be, because the increment instruction, so the addition, the immediate addition, will happen concurrently. And we don't know if the increment will happen like a split second before or a split second after the load. So at this point in time, we have no way of knowing if the value is 0 or 1. So, and that means when core number 1 stores its value, it doesn't know if counter will have the value 1 because it just incremented the variable, or if it has the value 2 because at the same time core 0 also tries to increment the function. Yeah, and this is actually pretty bad, and this is what we call a race condition, because basically the two threads are racing against each other, and it's unclear which of the two threads will win. So one might actually assume that finally, when core 0 stores the variable, that it should ultimately be have the value 2. But as a matter of fact, we don't even know that, because on most platforms, race conditions cause undefined behavior. So once you have one of those race conditions, then you really don't know what's going on. Like there are no guarantees by the operating system or by your programming language's runtime. For those reasons, race conditions are obviously something that we want to avoid. And it's also worth noting that there are even certain instructions, like the x86 read, modify, write instructions, like that operate directly in memory, where one of the operands is directly in memory, so we don't even have to load it from a register. And one could assume that such an operation that doesn't require an explicit load might actually be atomic, but it just so happens that even those instructions aren't atomic. Another situation where we have to be very careful about what we do, and that we sufficiently synchronize our operations, are accesses to shared data structures, like the vector data structure here, which has a function empty, and then has a function pop to remove the topmost element. And if the vector isn't empty when we query it with this function, but the function is parallel, so other threads might in the meantime have popped. It might just so happen that the vector is empty when we actually call pop. We pop from an empty data structure, which might cause memory access violations. And in order to avoid that, we synchronize those parallel functions in those regions where potential accesses to shared data structures happen. And we do so by obtaining locks. And after we obtain that lock from our thread function, execution becomes serial. And then after we're finished accessing those shared data structures, we release the lock again. And in general, this type of code block is called a critical section. Like we have our parallel function, and then generally the code there is executed in parallel. Like everything that happens here is not synchronized with all the other threads that also call this parallel function. And then we obtain a lock, access our critical section. Then comes serial code, which the critical section essentially really serializes the code, the following code execution. And then we leave the critical section, and things become parallel again. Apart from critical sections, there are also a bunch of other synchronization mechanisms, and we'll now discuss a few of them. One synchronization mechanism is a barrier or a fence, and barrier and fences are quite important because they are also used by GPU APIs that we will discuss later. And they are actually pretty simple means of synchronization, and they work by just setting up a barrier, and we tell the barrier initialization function how many threads we are waiting for. And then in our parallel function, we just wait on the barrier, and the instructions that are executed before the thread arrives at the barrier are executed in parallel. And every thread that arrives at the barrier waits until none threads waited at the barrier, and then all threads start their execution in parallel again. So this is a very easy to use way to synchronize threads. Another more resource-centric synchronization mechanism is the semaphore. And the semaphore is basically a wait and notification mechanism. Like you have one thread that initializes the semaphore and then does some work, and at some point the thread decides that it is ready, and then it notifies all the other threads that are waiting at the semaphore, and only then can the other threads resume their work. And internally, semaphores are basically just integer variables. Like in its simplest form, semaphores are just binary variables, and internally there's a count associated with the semaphore that is incremented and decremented, and depending on the state of the barrier, the threads will know if they can resume their work or if they are notified, etc. What I'm showing here is like the most simplest form of a semaphore, where you really have only two threads. What is worth noting about semaphores is that they are usually implemented by means of CPU interrupts. Like this is not a necessity and not exactly guaranteed by the APIs, but it's quite common that CPU interrupts are used. With that, they are pretty much the opposite of what is called a spin lock. And what is a spin lock? A spin lock is a very similar synchronization mechanism. Like what I'm showing here is a binary spin lock, but you can also have integer and counting spin locks. But a binary spin lock would be implemented by means of a Boolean variable, and we again have a main thread and a worker thread. And the main thread, at some point in time, notifies the worker thread that it can finish waiting, and for that it atomically sets the Boolean variable to true, like with a critical section or with an atomic operation that we will learn about later. And the worker thread uses a spin lock, as it just performs busy waiting on the condition variable. Like it uses a loop that basically does nothing other than querying the condition variable over and over and over again. So, and by that it obviously wastes energy on the CPU that it is spawned on, that the thread is spawned on, because it performs operations. It retires those comparison instructions. I mean, why is this worthwhile? This is worthwhile because a thread that uses a spin lock for synchronization doesn't require a context switch to get reactivated. So the time it takes to reactivate the thread is actually pretty short, because the thread stays busy on the core that it is scheduled all the time, and in order to reactivate it, we don't have to like perform any copying from memory to registers or from registers to memory. While when we are using a semaphore, then we are pretty much guaranteed that the inactive thread will no longer be scheduled on the core, and in order to reactivate it, to wake it up, we have to perform a context switch. Like, as I said, there's usually no guarantee about how semaphores are internally implemented, and certain implementations, would be free, like to maybe use a spin lock for a few cycles and only then send the thread to a deeper sleep, like so that that it actually uses interrupts and context switches in order to be reactivated. Like the implementations are relatively free about what they do, and like if we know that the thread is only going to wait for a few cycles, then it might be an option to use a spin lock instead of a semaphore. Nevertheless, like even when it might not make much sense to use spin locks in real life, because usually you can get away with semaphores, pretty much get away with semaphores. Nevertheless, they're kind of illustrating in a very nice way what a semaphore effectively does. Yeah? Like the two examples that I showed you, apart from how threads are scheduled and how threads are active and what work is performed on the cores, the behavior of the two synchronization types is pretty much the same. And another means of synchronization are so-called atomic operations. Atomic operation is one where there is guaranteed that it happens in a way that no other thread can interfere with the operation. Like the race condition with the counter variable that I showed you earlier. When we use an atomic operation for that, it is guaranteed that there will just be no race conditions. And typical atomic operations are atomic addition, atomic increment. Atomic compare and swap is a very common operation where we perform a comparison operation, and based on the comparison operation also perform an assignment. And depending on the API, this is implemented can be implemented differently. Like certain APIs actually expose those functions where you have functions that are called like atomic add or atomic increment. And those functions operate on ordinary integer variables. And other APIs express that by making the actual type atomic and then overloading operations. And those operations are then implicitly atomic as they operate on an atomic type. So regardless of how the API works, atomic operations are provided by the hardware, and this is what makes them different than critical sections, as they are a means that is provided by the actual hardware. Atomic operations can actually be quite fast and lightweight. The only caveat being that they, under some conditions, can have a very negative influence on caches. So let us now briefly put multithreading and Zimbi into perspective. Like Zimbi that we learned earlier about had this execution model where all instructions were performed in lockstep, and we had parallelism through the Zimbi width, the width of the vector of the register that we fit those scalars in, and that the instructions were performed on. And when the data path of our program diverges, what we do is we mask out certain lanes and have the Zimbi lanes only, or the Zimbi operations only work on those items that are currently active, and the other divergent paths we would perform work on afterwards. So threads, in contrast to that, are like fully concurrent. They can diverge completely. But on the other hand, they require synchronization, so we have to take care of synchronization. And the control flow and the data path of two independent threads can theoretically diverge completely. Like just think a multi-user OS where you just have, or a multi-process OS where you have different processes that are scheduled at the same time, and they perform completely different tasks, and they do this completely independent of each other. There are caveats though, like when you have a program where multiple threads work on basically the same task, and they diverge too much, then you can have all sorts of effects like caches having items that are invalid for other threads that also work on those items, etc. So you can have other issues that are caused by diversions that are undesirable, but generally threads allow for completely divergent code paths. So multithreading and Zimbi are orthogonal paradigms in that you are pretty much advised to write your program in a sense where you use both multithreading and Zimbi.
especially if you want to achieve maximum performance. And both paradigms are very important, like because what we're currently observing is that we're seeing architectures with wider Zimbi lanes and also with more cores. So understanding those principles and understanding the paradigms and and the programming models is actually pretty important to achieve maximum performance. So far we kind of assumed a model of operation that is pretty symmetric. Like we know that we have like multiple cores and multiple processors, and we just assumed that the memory that is accessed by those cores and that by those processors is like a shared memory pool, and all those cores have access to the memory pool, and memory accesses to the pool have about the same costs no matter which core accesses them, yeah. And on certain architectures, on SMP architectures, on symmetric multiprocessor architectures, this is actually true. But today's architectures are predominantly so-called non-uniform memory access, NUMA architectures. That means that memory is like physically distributed across the processors and cores, and those processors and cores have their own local memory, and when they perform accesses to the local memory, that is faster as when they perform an access to a neighboring or to one of the other processors or cores. Like we have local memory accesses on the one hand that are rather cheap, and we have remote accesses on the other hand that have a relatively high latency because they go through some type of interconnect. Like this is a very simplified illustration of what such a NUMA system can look like, where we have two CPUs, and each CPU is equipped with two cores, and each CPU has its own local DDR memory. Yeah? And then there's a bus that serves as an interconnect between the two CPUs. And as you can imagine, when CPU 0 accesses its own DDR memory, and this is faster as when it would access DDR memory that is owned by CPU 1, because the accesses go through the bus. And then, as you can see, as another layer of complexity, there are also caches associated with the cores, and we will talk in a later session why those caches are also connected with the bus here. And this type of simple bus technology is actually implemented by many multi-core architectures today. And when we have architectures like these, you can imagine that synchronization is actually pretty complicated, especially if we have caches and the CPUs and cores have to take care of that cache content is valid or is appropriately updated whenever there are accesses to local or to remote RAM. There are actually much more complicated topologies than the simple bus architecture that I just showed you. Like for example, ring buffers. Like in the first session, we briefly talked about the Intel Xeon Phi and the Knights Landing architecture, which were special coprocessors by Intel that were relevant in like 2015. This architecture is by now superseded, but it's actually pretty interesting architecture and looked a bit like this, with a ring buffer and multiple processors with multiple cores connected to that ring buffer. And as you can imagine, the memory access latency when you have a remote access to the memory of another core now actually depends on the distance to this core across the ring buffer. And you can also imagine that this makes optimizing for such an architecture much more difficult. Like back in the days, architectures were actually much simpler. Like a typical architecture from like 15, 16, 17 years ago would look something like this, where you had the CPU and then you had the chipset with the frontside bus, connecting the CPU to the chipset, and the memory controller being part of the north bridge, and all the peripherals connected via the south bridge, except for like faster peripherals like graphics cards, etc.
And then you would have a uniform way to access memory through the memory controller. Like architectures pretty soon moved the memory controller to the CPU, and also later integrated parts of the chipset into the CPU. But when we compare that to architectures that are around nowadays, they look a bit more like this. Like this is an Intel Sandy Bridge processor configuration with two processors uh, from around 2013, 2014. And those architectures were actually quite a bit more complicated and are also quite a bit more complicated today. Like you can see, we have multiple cores, and each of those cores is equipped with its own L1 memory and also with its own L2. So you actually have a hierarchy per core, and then you have a shared L3 memory. And then you have that ring bus that we talked about earlier that connects the cores. Like so, you have already on a single CPU, you have so much complexity. Then you have a memory controller per CPU. You have an I/O controller, so the chipset is pretty much integrated into each CPU. And then you have this complicated but very fast, very high bandwidth interconnect QPI that connects the two processors. So you have even on commodity machines like on those server CPUs, you have quite complicated architectures nowadays. And the problem that arises with this type of architectures is actually what happens when you have two processors and one of the processor holds a data item in their cache, in their local cache, and that data item is modified. And there are protocols out there, or there are protocols that are implemented by the CPUs, and they're actually implemented by functional units on the CPU. Like they are not implemented in software but in hardware, and those functional units implement something that is called cache coherent NUMA, CC NUMA. And what does it mean? That means that the CPU pretends that caches aren't local and there is no cache or memory hierarchy. The CPU pretty much pretends that there is only one memory. And whenever there are accesses to the memory, the hardware takes care of that memory items are valid when they are accessed, and also the hardware and those functional units takes care of that invalidation of memory items, and that communication over the bus, which is potentially costly, only happens when this is necessary. The protocols involved with it are actually quite clever, and those protocols we are going to talk about tomorrow.